Hi, my name is Lakshya Jain, and today I'm going to be talking about expressive robot behaviors and robot perception, along with robot learning. And the other topics that I'm going to cover are emotions, empathy, and AI, and how all of these relate to each other. There's also a section about language. All right, so let's start with the presentation now. Yep. So the agenda for today is I'll start with the introduction. I'll talk about expressive behaviors. I'll talk about robot learning, learning approaches that robot learning uses. I'll then talk about language and how it relates to semantics and how everything else relates to language. Then I'll talk about emotions, empathy, and AI, and then go over some related works, overlapping ideas, and then I'll do some discussions. So, starting off, what are expressive behaviors in robots? So, expressive behaviors in robots, I would define, are as actions or movements that convey some information that normal actions from robots that we have right now don't. And these are information or emotion or whatever kind of expressive outputs that robots can give to enhance a human robot interaction. Now these can include gestures, postures, sounds. It could also just be some random movement of the head or whatever part, and that conveys some kind of emotion. So it doesn't feel like not natural, it feels more natural that way. And you could these behaviors make these robots just more lifelike and relatable instead of all the disturbing and uh, sc- robots that will make you scared of them. That's not what the goal of robots is. Um, the goal of robots is to work with humans and to make our world better places and to make our lives easier by doing the things that we don't really want to do every time. They can do that. So that's what I think the goal of robots is, and they shouldn't be as scary as they are right now. So, um, so this is one of something that I've been working on, one of my projects. So this is just a robot head that shows different uh, emotions. It imitates my face emotion basically. And this is a demo from a TED talk that I saw. So here, the expressiveness of the robot is shown by the head movement right now. So we see that in the first part of the demo, the robot is not looking at what it's doing. It's not looking at the bottle it's lifting, so that the human that's working with the robot doesn't really understand what the robot is going to do. The human can't anticipate what the robot is going to do next if the robot is not looking at the object. So looking at what you're going to do, building up that anticipation for people around you is also a part of expressiveness of a robot, I believe. And uh, adding those kind of features will help bring robots to our day-to-day lives. So right now we see only robots only doing like factory work where people are not present. So robots kind of present a danger to people, and usually at warehouses or whatever, robots don't um, collaborate with humans actively, because one, that they are not compliant enough right now, and also two, that they are not expressive enough to make the human coworker be able to understand what the robot is going to do next. So those are the issues that are there. And adding expressiveness to the robots, as well as maybe making them soft robots at some places or parts, would help for uh, this is a graphic of all the different kind of research that are going on with human robot interaction, path planning, navigation, human aware systems, multi-agent systems, as well as all the research that's going on in these fields. I feel there is a certain lack of uh, adding logic to the perception models that we have right now, and using language to bind everything together, and also adding emotions, expressiveness, as well as uh, empathy to the robots that we're building. So all of these areas are really good areas, but we should also look more towards the social navigation part, and maybe build forward towards this as well. So what is robot learning? So robot learning is going to be my next topic that I'm going to talk about. So robot learning is just a subfield of artificial intelligence and robotics, that for it's basically machine learning but for robots. So uh, it focuses on giving robots the ability to learn and adapt through their previous experiences, and cumulatively learn through these experiences. And these are not like explicitly programmed actions for each specific action, like if else loops. They are learning through um, their data sets or their past experiences, or through supervised, unsupervised methods, or through trial and error. The ultimate aim of robot learning is to just to enable robot to do uh, complex and even unpredictable so even handling unpredictable events, and doing tasks that it hasn't done before, or making things connecting things that it hasn't seen before. So that's something that humans do all the time, and robots can learn in the same way as well. So it's a IO inspired approach. Generally, learning artificial intelligence is mostly built in the image of humans, of how we think. And similarly, we're trying to make robots think in the same way. Now, this capability would open up a lot of new applications in industries like manufacturing, healthcare, service, exploration, and we know all of that. And we can like make robots that think like humans, that can express like humans, and they can empathize and also show emotions like humans, and they can operate in dangerous situations which are inaccessible to humans, like if you want to defuse a bomb, you would rather send a robot than a human. And there are certain places that are highly inaccessible to humans, like cave systems, or other places like deep sea or deep space. Robots would have an easier time exploring those places if they're autonomously able to navigate those places. And if they have similar perception to what humans have, or better, it would make robots a lot better in those situations. So yep, moving forward, so robot learning and machine learning, um, so these are different types of learning like these are different types of learning algorithms that are being used right now. So supervised and unsupervised learning algorithms are mostly data driven. So they have like data sets, Supervised learning algorithms have labeled data sets. So uh, everything has to be labeled either manually or by uh, semi supervised, like a machine will label them, but then a human will be supervising the machine. So there is labeled data sets usually in supervised learning. um, there is also unsupervised learning where there is just a data set and nothing is labeled or whatever. The machine, the computer is supposed to uh, segment these into different types of data, but then when the segmentation happens in unsupervised learning, usually you don't really know what the data means. So you have to still make a human work with the robot. The other two types of learning that are there, reinforcement learning and imitation learning, are very bio inspired. So I'll focus more on those right now, because supervised and unsupervised are pretty common um, ways of learning. So reinforcement learning is in a kind of a buzz right now, and so I'm gonna focus on reinforcement learning first. So reinforcement learning is basically a trial and error function algorithm, which makes you learn through trial and error, like what a human would learn like. So I'll show you an example of what this means. So many uh, reinforcement learning algorithms are used to mimic real world biological learning methods through positive reinforcement. So basically, there is a reward function that would give you a positive reward if you do something that is done right, and if you do something that is not done right, it'll give you some kind of a negative feedback. So it's just a feedback loop, and it just keeps rewarding you if you do some things right, and if you don't do some things right, it doesn't reward you. So that's kind of basically what humans learn like, right? So uh, like reinforcement learning differs from those first two, supervised and unsupervised learning, because it doesn't really need a data set, and it doesn't really need labeled output input pairs to be present. And it's more of a sequential learning method where you do some task and then you get an output, and then you get to learn what's good and what's not. So let's focus on an example about reinforcement learning now. So suppose there's a baby is usually developing. uh, it's more of not knowing everything, but it's developing, it wants to know everything. So uh, let's start with the example of a baby that's sitting and it spots a bottle. Now the baby is hungry and it wants milk, and there's no one around him. So there's two ways a baby can approach this. Maybe he'll start to cry, or maybe he starts to crawl towards the bottle. So till now he didn't know how to crawl, but then he just starts moving his arms and feet around because he's seen uh, people do that, and then eventually he'll be able to crawl over to the bottle, and now the baby can lift up the bottle, drink from it, and now the baby is happy and not hungry anymore. So that is a cumulative reward that the baby received for learning a behavior that is crawling. So similarly, we can teach a lot of these behaviors to robots, and I'll show further that some of these are being done right now. So let's move to the next example. It's the same baby. Now he's drinking that bottle. Now he's sitting. Um, he's pretty happy already, but now he sees a toy um, that is placed on a little higher level than what he is, uh, you know, used to while crawling. So now he's learned to crawl for a long time. Let's say he's been crawling for 2 months already. Now he sees that toy that's being placed on a drawer that is slightly higher than his height, and he has to reach up to get it. The baby hasn't stood up onto its legs yet, so now he sees the toy, and the toy is the reward, and happiness is also the reward. And so basically, he tries to get up and tries to get on his 2 feet. Um, and when he reaches the toy, if he succeeds in reaching the toy, uh, that means he has reached the reward. He has successfully learned a new behavior, and he has reached a reward function. So he's gonna be rewarded by being happy, and he gets to play with his toy now. So that's pretty good. And this is also an example of reinforcement learning. It's pretty similar to the last one, but I just thought I'd add one more example just to preface this. And also, when babies learn to walk, they have their parents around them, and parents will show happiness, which the baby will think of as a reward function. So whenever the parents are happy, the baby is also happy. So that is a reward function. So that was a reinforcement learning, which is a reward based learning system. Now let's focus on imitation learning. Imitation learning also uh, is a very bio-inspired approach of learning. So usually, as babies, we hear a lot of people talk around us, and eventually, like after like a year or so, we start catching up on words, and we start making sounds from our mouth that that we try to imitate from watching people around us. So these behaviors that we start demonstrating are an example of imitation learning. So we watch people talk, we watch people walk, and we try to replicate that because we have the same body as them. Why can't we do what they do? All right. So this is imitation learning is another kind of learning, and it just is using your own body to do what you see or you perceive. So by hearing, by seeing their lips and tongue move, you can pick it up pretty quick. So humans pick up language pretty quick when they're young, and that is a way of imitation learning. So there's two main approaches in imitation learning. One is behavioral learning, where the agent uh, directly maps the states to actions, and that is uh, the first way. And then the other way is inverse reinforcement learning, which is the opposite of reinforcement learning, where the aim is to learn underlying reward function and then expert so in this case, these women who are talking are experts at language, and then we are just observing the reward function uh, that they have underlying, and that's how we maximize our output from imitation. Okay. Now, how can we teach behaviors? How can we teach robots to do expressive behaviors? I went through a research paper from Google DeepMind recently. So when it comes to teaching expressive behaviors to robots, reinforcement learning is very useful, and it can enable a robot to learn the most appropriate empathic behaviors to different states that we put the robot in or we present the robot with. And this framework that I was going through is called generative expressive motion. So it basically uses a large language model, which I'll be going into further. So it uses a large language model, not a single large language model, but like four different modules using large language models to autonomously generate expressive behaviors for robots. Now, imitation learning can enable a robot to learn certain interactive skills by learning from video observation and then applying them to their real life human robot interactions, and also maybe robot robot interactions. I don't know about that, but in the future, maybe. So the paper shows the workflow that they were using. So basically, they start with an expressive instruction uh, that is just description of a scenario that the robot finds itself in, and then you translate that into a human to robot expressive motion. So what would a human do in this case, and what would a robot do with robot capabilities that it has? So this is sent as a query to a GPT model. So GPT model is something that's very popular right now. Um, and and GPT is called a generative pre-trained transformer. Transformer is another one of uh, Google DeepMind's research papers that was very influential in this field of artificial intelligence. And after the Transformers paper, there was a lot of research in language that was able to be done, and then language has been the forefront of AI right now, and um, language is pushing AI for a very far limit. I'll be talking about language further in this presentation. So human to a robot expressive motion is then converted into robot expressive motion, and then into code. So they generate a code from this robot expressive motion, and then they send it to the robot, and then robot does the action, and then they give it a feedback from the human that they were doing this with. So using the feedback, it uses reinforcement learning to make the actions better for the next time. So this is an example of uh, how we can teach robots to do behaviors, but this can go even further. So now the next topic I want to talk about is robot perception and how it relates with language. So robot perception right now has a lot of sensor fusion involved, but um, as far as I can see right now in the state of the art, it's mostly not related to language yet, because we can add a lot of logic to how robots perceive the world using something like language. And because language models are at such a rapid growth right now, I think in the next few years we'll have a lot of language in everywhere. So our ability to understand is limited by our ability to perceive, and similarly robots ability to understand is also limited by the ability they can perceive with. So perception systems right now, with the slam and metric semantic slam and all the other innovations that's going on, are at a pretty good uh, point. But the inclusion of logic and language is not there yet. Now, what I think about AI is that AI turns a semantic relationship into a geometric relationship. So I'll give you an example for this, and I'll tell you what semantic really means. So, semantic really means the meaning of a word in a language. And I think semantics are a bridge between language and visuals as well. So, when you have a visual of something and then you have semantic information about it, you can relate it with language very easily, and then vice versa as well. And now I think AI turns semantic relationships into geometric relationships. How does that work? Let's say we represent points in a language as words. So there is a word called king in English language, and then there's a word called man in English language, and similarly, queen and woman is there. So there is a vector moving from king to man. So that is in one direction. Um, there is a vector that goes from king to man, and similarly, if we draw the same vector from queen, we land at woman. So if we take king, subtract man from it, sorry, if we take man, and then if we take king and then subtract a royalty from it, we get man. If we take man and opposite of man, we get woman. And then if we add royalty to it, we get queen. So this vector is represent a semantic relationship that is royalty. So going from king to man, we have some vector, and then going from the other word to another word, we have some relationship vector that relates the two words. So we can express language as points in space. So this doesn't have to be a 3D space, it can be any dimensions, n dimension space, but we can represent a language as an n dimension space. So let's express language as a shape right now. So let's showcase different languages that we have as shapes. So these are like the top 10,000 words in Spanish, English, and Japanese, represented as shape. So as you can see, those shapes look very similar because they're all human languages, and they are mostly made on top of the human experience. So human experience everywhere is mostly very similar. So we have those similar associative connections between our words as the other languages that other people use. And if we take a word dog and then we point it out in every language, we can see that dog um, almost overlaps. So wherever these languages overlap, dog is at the same spot in every language. Even a very different language like Japanese and English, they have dog at the same spot, which is very, very insightful. And we can make with that means that we can make a lot of associations with objects, with and between all of these things: objects, words, spaces, concepts, and contexts, and emotions. Maybe emotions are concepts. So we can make those relationships with language and visual information. And if we have these informations, we can make our perception systems a lot better than what they are right now. Language and AI. So this is what I've been talking about for a very long time right now. So language models right now are doing a lot of things. So um, previously, all of these things, all of these fields in AI were perceived to be like different fields. They were approached very so they were approached very differently uh, before language played a really important part. After that Transformers paper, language picked up, and then language eventually uh, took part in all of these. So the control of robots, music, sound, images, all of these are related to language, and language acts as um, like a glue for all of these in AI, and we can approach all of these problems using language and a lot more problems. So right now we're just using natural language. We can also look into other animal languages and non-human languages, which is a completely separate field, and I won't be talking about it in this presentation, but that's a really profound field. So let's go to my last topic, that is empathy. Now, um, you would think giving a robot emotions and empathy is just not real emotions, they're just emulating things that we program into robot, and then the robot shows us some expressive behaviors or whatever. But mm, it's not really authentic, right? Let's move into what authentic really means. So according to Merriam-Webster, authentic needs two things to work. One is that it's able to reproduce essential features that the original had, and it's done in the same way as the original. So those things make it authentic. And I think we know a lot about the human brain and how it works, and how emotions and empathy work in our brain. And we can build the same things in robots, and that would technically be authentic. And who's to say it's not authentic, right? So if we build empathy into robots, so there's two types of empathy that we know about: cognitive empathy and affective empathy. Now these what usually human psychologists would say, that someone with no affective empathy would be classified as a psychopath. And if our robots don't have affective empathy, we would classify them as psychopaths. Why do we need psychopath robots in our houses, right? That's not what we want, right? So I think moving forward, we should also build empathy into our robots. So there's a lot of things that I talked about today that we need to build into our robots. One is that we need to integrate logic with the perception models that are currently there. Two is that we need to um, build connections using language, and make everything work together using language right now. Third is to have empathy and expressive behaviors into robots, and language again acts as a very important part of that, because language is how we define or express those things, and there is always words in language that can describe what is going on usually. So those are the areas we need to explore in robotics. That is it for my presentation, and thank you for watching or listening.